Hello, my name is Uğurcan Akdemir, and this will be the second part of our Kakuro Solver artificial intelligence presentation. For our second approach, we've chosen to use logic because it is somewhat intuitive to actually use logic to solve this game. It fits. So we know that logic-based artificial intelligence should mirror human thinking. It should be somewhat similar at least. And what do we mean by that? Well, let's talk about how humans solve puzzles of Kakuro. On the picture on the left, you will see some white little markings on the white cells. Those represents the values that can be placed in those specific cells. The top leftmost one has 1 and 3. That means that 1 and 3, 1 of 1 and 3 can be placed there. And if, for example, 1 was placed there, the cell at the bottom, cell 1 below it, would have to take the value of 3. So we know that any values other than 1 and 3 cannot be put there. And the same goes for all the other ones, all the other cells. Now, as a human, we can intuitively, basically calculate how many values these different cells can have based on the rules. But making a computer do that is a little harder. So we've chosen pretty much the next best thing. Let's go on and see. Now, we're still using a two-dimensional integer array as the gaming board because that's just easy, whatever you say. Now we've chosen to create some files and fill them with, some folders and fill them with specifically named txt files. Now the names of these folders are, well, they go from 3 to 45. You will understand why later. And the the text files inside are named after, are named 2 to 9. Now, why did we do that? Well, one of the reasons, well, the only reason we've actually done that is because the folder names represent the possible constraint values in Kakuro. We can go from 3 to 45. Why not 1 and 2? Because, well, if you have a 1 as a constraint, you need to have a single cell where that constraint is in effect. That's just not really possible. And if you have 2 can only be divided into 2 once, and 2 of the similar integers on one row or one cell just can't be accepted. Another question you might ask is, why is 45 the upper limit? Because if you add together all the numbers from 1 to 9, 1 and 9 included, you get 45. Well, since we only have 9 one-digit numbers, that's the upper limit of what we can do with them. Now we've chosen to name the text files after the number of cells. Sorry, let me say that in a better way. Let's say that we have a constraint. Let's say that it's 11. We need to find out how many different ways 11 can be achieved with n cells, n variables. Now, we already established that we can't have just one, right? Because that just wouldn't make sense. As for 2, yeah, we can add 2 and 9, and that would be 11, and some others. Those are just the combinations. So the text file named 2 would contain all the possible ways of adding up two numbers into 11. 11 can also be represented as a combination of, for example, three variables. Because of that, there is a file named 3 inside the folder named 11. So basically, we've created a folder tree where every single leaf is a text file that contains the number of cells that we would have to have on a Kakuro board. That way we could search through them with a simple file opening and line reading mechanism. And we'd be able to do a couple of things with that. Now, Python uses strings to create directories into which the files will be placed. We had to do that with some string manipulation that we will talk about a little further into the presentation. Now, as we talked about, the text files contain not just 2 and 9, because 2 and 9 isn't enough. There is also 9 and 2. So every single permutation is contained within those files. Now we have a couple of functions that we will just read the names of now, and we have slides of their own coming. We have the populate first function. It is almost completely the same as the one my friend Ergin talked about. We have the isGame, the game state checker function. It is practically the same. We have a generate file name function. It does some string manipulation and gets us a file name, the txt file name, as well as its directory, so we can reach it faster. We have a fill row function. It basically takes the file name and fills a row with it. The last row is almost completely the same. We have to do some backtracking, and we have to go back one row, and that's where the last row comes in. Solve game is the function that does everything and calls all other functions. Now, populate first. It's almost completely the same as the populate first function in the previous one, but in this one we don't just go for all the possibly smallest values. We instead go for some permutations that are stored in our files. Its argument is the board. That's obvious. This one uses a folder network as the one we talked about previously. We have gone on more detail on the folder network on our presentation, the project report. If anyone is interested, you can take a look at that. We have the isGame function. It is the same as the one from the previous approach. Well, basically, for a game of Kakuro, game state of Kakuro to be eligible to be called a finishing or game ending state, or whatever you would like to call it, every single row, every single cell in a row had to be combined, and that combination would have to equal to the horizontal constraint, which is the x0 on the gaming board. And the same also goes for all the vertical constraints on the 0th row of the gaming board. We have probably talked about that before, so we'll pass that now. Now, generate file name, as we said, Python and probably every other programming language that has the capabilities of opening files uses a directory as to be able to know where the files are. So yeah, this does that. In Python it is extremely easy to just use the plus operator and concatenate multiple strings together. We do that, we add some forward slashes where it has to go, and we also have a variable that is just .txt as a string. We add it to the end of everything, and we have our directory name. The fill row. Fill row calls the generate file name function. It gets the file name that needs to be the file's name that needs to be opened, and it goes there and opens the necessary text file. Well, it then reads permutations of these subsets and places them inside the row that it is currently pointing at. And it does this in a couple of steps, and we know that every single file in our file jungle has an end of file character that is placed at the end of the file, and when that character is reached, this function is terminated. We have the last row function that is pretty much the same as the last row function from the previous approach. It points us to the previous row. We use it to backtrack. The solve game, it does everything. It basically solves the game, and it is probably the most important one, and also probably the most wasteful one. Now, how do we go about solving a game of Kakuro using the logic approach? Well, we populate the board with the smallest values possible. And how do we know we have the smallest values? Well, because we have arranged the values inside the files to go from the smallest one to the largest one. It doesn't really matter all that much how big or large they are, because pretty much all of them will be tried. Now, after populating it for the first time, we check if the current state is a game ending state, on the off chance that it is. It almost never is. Then the solve game function is called. It calls the fill row function and starts refilling the board. The board. Now it goes about. It's from the bottom up. It draws one value from the file, puts it in the bottom row of the board. The game is checked. The game state is checked. If it is not game state, that same fill row function pulls the next permutation from the file, places it into the board, and the game is checked again. If we reach the end of file function, it means that the problem of the current game state isn't at this particular row, and that we have to go back in deeper, backtrack a little bit. So we do that. We go on to the row that is one above the current one. We open the files from the fill row function. It generates a new directory using the constraints name as well as the number of cells in that row, and we change it. We change the value of the current row once, and then we go back down and start changing the value of the start trying every possible permutation of the apparent solution. And when the second from last row is also completed, we know that the problem is higher up, and then we just jump back up and complete all these steps together. And in the end of it, we eventually reach a solution state, because well, obviously we have all the solutions. We know that one of them is true. We just try every single one. Now, we understand that this is a pretty brute force-ish method of going about things, but it is somewhat informed. It is actually, well, practically, it is much better than a simple brute force method. Anyone can basically do that. But on paper, the time complexity is pretty much the same as the brute force method. It is not perfectly efficient, but it is, again, still better than using simple brute force. Because every single thing we try has a very high chance of being the possible value. At every single step that we take, we spend less time than the brute force approach. It is a pretty good thing to be able to do that. And even if it is on the paper not all that efficient, well, we still have the previous approach that we've done. It is basically brute forcing our way through without actually brute forcing it. Now, on the previous approach, we have always checked if what we're doing is consistent or if there are any inconsistencies. Because once you go beyond the value of the constraint, well, everything else you do until you exhaust every single one of the possible values you have, well, that is just a waste, and we wouldn't want that. But we don't really do that here. Well, because we don't really need to. We know that uh, we have an answer in our hands, and the small amount of time we waste searching for it can't exactly be recovered by checking if there are any inconsistencies. It is simply unnecessary. And it might actually be somewhat slower to check for inconsistencies, because even if there are inconsistencies, when we get the next permutation, that the parts of that permutation that creates an inconsistency might be much smaller, right? So checking an inconsistency and trying to make sense of all these permutations doesn't exactly make all that much sense. So that's why we don't do that. And as I said, was the logic approach to solving Kakuro. My name is Uğurcan Akdemir, and I thank you for listening to us. Thanks again, and hopefully see you.